composition matrices, what is the point of them? Maybe you want to take a shortcut. Let's say you need to transform an entire set of 100 numbers from A to B, and then from B to C. You can do this process for every single vector you need to transform, or you could just create one matrix. You could multiply the set of vectors in A to get C. You won't need to do two steps, especially if you find the bases, because if you find the bases, then you figure out how to transform that from one, figure out how to transform a basis vectors from one linear transform to another into one instead of doing them twice, then you can just map an entire vector space through two transformations in one go. So composition of matrices is a very good idea. You should definitely pay attention. So the composition of matrices is when you combine matrices that represent a linear transformation, but this will only work if the codomain of one linear transformation matches the domain of the second linear transformation. What do I mean? Okay, let's say we've got a function that maps our set A to set B, and this is how we'd represent it. So this is our codomain, and this is our domain, because as you have hopefully seen my last video on how to do transformation matrices and how to represent them, and how to find the bases and so on, all of the vectors in this matrix are A in terms of B. You can think of it that way. And it's the same there's the same story over here. So yes, they need to match. So in order to multiply these two, you go GCB times FBA. And then, this would be the notation, you would say that this is G of F. Or you could put it this way. So the image, essentially what's happening is that the image of the first function is being put through the second function, which give an image of G. This is a double whammy because it's an image of an image. So you can see you've got the image of FA, but then G takes the image of this and makes it an image of G. So to find this, all you have to do is find the transformation matrix of this, and of this, make sure that domains and codomains match, and you're done. So essentially composition functions are well named because they're composed of two functions. Let's do an example. So let's say we've got some f of xy and g xy, and these are our bases. And the question is, what is the matrix of g of f with respect to b and d? So find g of a for all b and d with respect to t. That's how I've written it. I don't think that's mathematically correct, but essentially what you're trying to do is find a matrix that's in terms of these two bases vectors, but takes into account both of these transformation matrices. Okay, so first thing we need to do is find f of cb. So we find image of all the basis vectors in terms of c. So what is v1? It's 1, 1. We put it through the transformation matrix and we get 2, 0. And then what is this in terms of c? It is 0, 2. And we repeat the same for our second vector. And this is the transformation matrix, which we get. So we've got f of cb. So now find g dc. So the image of all the basis vectors in terms of d, so whatever the first basis vector is of c, we put that through g. Whatever vector we get out of that, we represent in terms of d, and we do the same for however many vectors g has, but in this case we can do it twice. So here's our transformation matrix there. So now we need to make sure that we match the codomain to the domain, so we have our g of f of xy. Then we just evaluate through matrix multiplication, and then this is our final answer. And this is all of the working out. So essentially what this matrix will do is transform any basis vector from B through here, through this, to D. It's pretty cool. Don't know if that makes much sense, but I'm sure it will if you do enough practice questions. So knowing this, we can actually integrate our knowledge on inverses. So we can use the composition of matrices to check if a matrix is invertible. But before we can even do a composition of functions, we need to check if the range is equal to the number of columns in the domain, and if the codomain and the domain have the same dimension. If they do, you can go for your life, find as many inverses as possible. And essentially, if you put the inverse of some function, like if you take the image, yes, it does run nuts in your brain. If you take the image of the inverse of this function, you should get x back, or the identity matrix in this case. So the inverse of a function, or the inverse of a matrix, as you know, they don't always look the same. You know, when you do functions, the inverse, you can sort of see the similarities, but with matrices, the inverses look very different. So in performing a composition of function transformation, you can figure it out if the matrices in question are in fact inverses. You might have to multiply them one way and the other way just to check, but if you get the identity matrix back, then your matrices are inverses of each other. So in summary, applying composition functions to matrices makes it fast to evaluate multiple transformations for a vector. You may want to rotate, stretch, and then flip a vector, and you can do this all in one go with a composition formula.